Welcome back to the deep dive. Today, we're diving deep into a concept that's truly at the core of Angular. It's often misunderstood, I think, but incredibly powerful: change detection. Our mission today is basically to take your sources and give you the shortcut, the real understanding of how Angular keeps your application's user interface perfectly in sync with its data. We'll explore why mastering this isn't just, a technical detail, but really a path to building smoother, faster apps. Think of it like uncovering the crucial behind the scenes magic that, once you grasp it, really elevates your development skills.
That's absolutely right. And this deep dive, it isn't just about learning technical terms. It's really about understanding a fundamental mechanism for building applications that feel responsive,
Hmm.
consistent to users, whether it's a simple counter or maybe a complex real-time data feed. If you've ever found yourself wondering, why isn't my UI updating? Or why is it suddenly so sluggish? Then,
Yep.
yeah, this conversation is definitely for you.
Okay, let's unpack this then. At its heart, what exactly is change detection in Angular?
Well, uh, simply put, change detection is Angular's way of synchronizing the view. That's what you actually see on your screen, the user interface with your application's underlying data model. When your data changes in your code, Angular needs a reliable mechanism, a way to update the document object model, the DOM, to reflect those changes instantly. That's its main job.
Right, and I found a great analogy in our sources that makes this really clear. Imagine you have a JavaScript object, right, holding a user's profile name, email, picture, whatever. These properties are connected or bound to elements in your HTML template. Now, when you update, say, the name property in your JavaScript object, change detection is that swift, sort of unseen process that instantly makes that new name pop up on the screen. Without it, yeah, you'd be stuck with a frustratingly inconsistent experience.
Precisely. And to build on that, the core principles at play here are, first, data binding. That's the connection, right, between data and view, either one way or two way. Then there's the change detection cycle. This is what Angular runs repeatedly, triggered by different events to check for changes. And finally, the component tree. Your Angular app is structured like a tree, a hierarchy of components, and change detection travels down this tree.
So, why is truly getting a handle on this process so crucial for you, the listener? Whether you're building an app or just want to be well informed, why care about this behind the scenes stuff?
Oh, it's vital. For several key reasons, really, all focused on delivering a better user experience. First, data consistency. The view always accurately reflects the data. That's paramount. Second, responsiveness. Efficient change detection means your apps feel fast, snappy. Third, and this is critical, performance. Inefficient change detection can make even, moderately complex apps feel sluggish. So optimizing it is absolutely key for a smooth experience. And beyond that, it helps with prioritization. Maintainability makes data flow easier to follow, and it's, frankly, essential for debugging when your UI isn't updating like you expect it to.
Let's bring this to life a bit, maybe with a real world scenario we can all picture.
Sure. Take an e-commerce app. If a product's price changes during a flash sale, change detection needs to ensure that new price updates quickly on the screen. If it's slow, customers get a poor, maybe confusing experience.
As for business.
Exactly. Or think about a social media feed. When a new post is added, or someone likes a post, change detection updates the feed instantly. Without it, you'd have that sluggish, frustrating interface, especially with lots of users and posts interacting. And what enables this immediate update is the change detection tree, which, like we said, mirrors your component tree. Each component gets its own change detector, forming this hierarchy from the root down. Angular visits them top to bottom, and that order. It has huge implications for performance.
Okay, so we've got a grasp on what it is and why it's so important. Now, how does Angular actually do this by default? You mentioned performance implications.
Yeah, that's the interesting part. By default, Angular uses what's often called a dirty checking strategy. It checks the entire component tree. Angular, by design, sort of assumes that any change might affect the view somewhere. So after every event happens, it checks all components in that tree.
Every event, that still sounds like a lot of work. What kinds of events are we talking about here that trigger such a wide sweep?
Good question. It's quite broad. The common triggers include user interactions, so browser events, clicks, key presses, form submissions, that kind of thing. Then there are asynchronous operations. Set timeout, set interval, promises, RxJS observables, but importantly, only when they're running inside the Angular zone. And finally, HTTP requests, like responses coming back from HTTP client calls.
Okay, the Angular zone, you mentioned that. That sounds important.
It is. This brings us directly to a key, maybe somewhat unsung hero, Zones, and specifically the library zone.js.
What exactly is a zone then? And why does Angular need it to pull off this automatic detection after async stuff happens?
Okay, so a zone is basically an execution context that persists across asynchronous tasks. Think of that like a smart wrapper, maybe, around JavaScript's async operations. It allows Angular to know when an async operation like a set timeout finishing or an HTTP response arriving is completed. Once zone.js notifies Angular, Angular can then automatically trigger a change detection cycle. Without zones, you'd literally have to manually tell Angular, hey, update the view now, after every single async action, which would be incredibly tedious and very error-prone.
So it's zone.js that intercepts things like set timeout. It kind of hooks into them.
Exactly. Zone.js uses a technique called monkey patching, basically. It intercepts standard JavaScript async APIs like set timeout fetch, XML HTTP request. When one of these patched APIs is called, zone.js gets notified, and in turn, it notifies Angular. That prompts the change detection cycle.
Ah, okay. So if I have a set timeout that updates some data property after, say, 2 seconds, zone.js makes sure Angular knows about that change when it happens and updates the DOM to show the new data, all automatically.
Precisely. It's designed for developer convenience. Makes life easier, right?
Definitely.
However, as you hinted at earlier, this default strategy, while convenient, does have its limits. It can lead to significant performance overhead, unnecessary checks, especially in larger applications with many components. And this is exactly why we sometimes need more granular control. We need ways to tell Angular not to check everything all the time.
Right. If the default strategy checks everything, and that can slow down big, complex applications, what's the next step? How do we get more surgical with our updates? How do we optimize?
That's where the OnPush change detection strategy comes into play. It's essentially a way to tell Angular for a specific component, hey, only check this component for changes if specific explicit conditions are met. Don't just check it because something might have changed somewhere else in the app. It's a shift, really, from Angular handles everything to I, the developer, strategically control when updates happen for this part of the app.
Okay, that sounds like a powerful tool for performance. So what are those specific conditions? When does an OnPush component actually get checked?
Good question. With OnPush, change detection only triggers under a few specific circumstances. First, if the components at input properties change their reference. This is key. It means a new object or array is passed in, not just that something inside the existing object was modified. Second, if an event originates from the component itself or one of its children, like a button click within that component's template. Third, if you explicitly tell Angular to check it using change detector ref, which we'll definitely dig into next. And finally, if an async pipe used in the template receives a new value from an observable or promise. Okay, this input properties changing their reference bit sounds like the real core of it, but maybe also the trickiest part. What does that mean in practice, and what's the most common mistake people make here? You've absolutely hit on the crucial point. And that's precisely where the concept of immutability becomes so vital when you're using OnPush. Immutability means that once an object or array is created, its state cannot be changed. Instead, any operation that looks like it's modifying it actually creates a new object or array with the desired changes, leaving the original completely untouched. It's a fundamental shift in how you handle data updates.
Can you give us that practical example again, the person object one?
Sure. So if you have a person object with an age property, instead of directly doing person.age equals 31, that's called mutating the object, you create a new object. For instance, const-updated person age 31. That person spread syntax, copies all the properties from the old person object into a brand new object, and then we overwrite the age property with the new value. The original person object remains unchanged.
Got it. So the reference changes because it's a totally new object in memory.
Exactly. And that is why immutability is so vital for OnPush. When data is immutable, Angular can perform a simple, super fast reference check. If the memory address, the reference, to an input object is the same as it was last time, Angular knows nothing inside could have changed because it's immutable, and it can confidently skip change detection for that component and its entire subtree. This skipping is where the huge performance boost comes from.
So that classic pitfall you mentioned, if I have an array as an @input on an OnPush component and I just push a new item into it?
Bingo.
Yeah.
That won't work. If you just use .push, you're mutating the existing array. The reference to the array itself hasn't changed, So the OnPush component won't detect the change and your UI won't update.
Ah,
You must create a new array. The common pattern is using the spread operator again, this.items equals this.items, new item. This creates a brand new array containing all the old items plus the new one, giving you a new reference, which will trigger change detection in the OnPush component.
yeah.
And yeah, libraries like Immer can help make managing immutable updates a bit less verbose, which is nice.
Okay, so OnPush plus immutability is a really powerful combo for performance. But what if? What if a change happens that doesn't come through an at input changing its reference or an event fired from within the component?
Huh.
Like maybe data arrives from a service that the component subscribes to, or a change happens deep inside an object that's passed as an input. How do I tell Angular, hey, you need to check this specific on-push component now without, turning change detection back on for everything?
Great question. That's precisely the scenario where Change Detector F comes in. It's a class provided by Angular that gives you fine-grained direct control over the change detection process for a specific component and its descendants. You get access to it by injecting it into your component's constructor.
Okay, so change detector. Let's look at its key methods. First one I see is detach. What does that do? Sounds significant.
It is significant. Detach literally removes or detaches a component's change detector from the main Angular change detection tree. What this means is Angular will no longer automatically check this component or its children for changes during its regular cycles. You, the developer, are now taking full responsibility for telling Angular when to update this part of the UI.
Right. When would I actually want to do that? Detach a component.
Well, a couple of scenarios come to mind. One is for components with infrequent updates or content that's mostly static. Think maybe a complex SVG chart that only updates when specific data comes in, or a static header. Why have Angular check it constantly if it rarely changes? Another really common use case is when dealing with external data sources or libraries that operate outside of Angular's zone. Maybe you're getting data from a WebSocket, or using a third-party animation library that updates the DOM directly. Since these might not trigger zone.js, Angular won't know to run change detection automatically. Detaching and manually triggering gives you control.
Okay, so if I detach it and Angular isn't looking anymore, how do I get the view to update when something does change?
That's where the other key methods come in. Detect changes and mark forecheck the
Yeah.
changes. Forces an immediate synchronous change detection run specifically for just the current component and its children. It checks the component right now. It's direct,
Uh-huh.
but if you call it too often, it can potentially cause performance issues itself. Mark forecheck is often the preferred method, especially when you're using OnPush. It doesn't run change detection immediately. Instead, it simply flags the component and all of its ancestors up the tree as needing to be checked. It marks them as dirty. This means Angular will include them in the next regular change detection cycle whenever that happens. It's generally safer and more efficient because it integrates with Angular's normal flow.
Okay, let's revisit that real-time data example. Say, a component showing stock prices from a WebSocket. How would change detector ref fit in?
Right, so you might detach that component in its ngOm init hook because maybe prices come in very frequently and you don't want constant checks triggered by other unrelated things. Then, when a new message arrives from the WebSocket, remember, this likely happens outside the Angular zone. Your callback function updates the component's data property holding the stock price. After updating the data, you need to tell Angular to update the view. You could call this .cdr.detectChanges if you need that price reflected instantly. Or maybe more commonly, you'd call this .cdr.markForCheck. This flags the component, and the new price will appear on the screen during the next regular Angular change detection tick.
Makes sense. And what about the last one, reattach?
Reattach is simply the opposite of detach. It plugs the component's change detector back into the main tree. So Angular resumes checking it automatically during its regular cycles. You might use this if, say, a previously detached component becomes active or visible again, and you want Angular to manage its updates normally from that point on. It's worth adding a little caution here, though. Manually managing change detection with Change Detector Ref definitely adds complexity. It's easier to make mistakes, like forgetting to call mark forecheck, leading to UI that doesn't update. Often, really leaning into OnPush and immutability first is a simpler and more robust way to tackle many performance issues. Change Detector Ref is powerful, but use it judiciously.
We've covered the core concepts, the strategies like on-push, and even manual control with change detector ref. Now, practically speaking, how do we actually find these performance bottlenecks related to change detection in a real application? And are there other big levers we can pull for optimization?
Yeah, finding the problems is key. Your absolute best friend here is the Angular DevTools browser extension. It has a dedicated profiler tab that's specifically designed for diagnosing change detection performance.
Okay, Angular DevTools Profiler. What should I be looking for in there? What are the red flags?
When you run the profiler while interacting with your app, you'll see a change detection timeline, often visualized as a flame chart. You want to look for a few things. First, look for bars in the chart that are very wide or long. These represent individual component change detection cycles that are taking a significant amount of time. That's a clear bottleneck. Second, look for components that appear very frequently in the timeline, especially if their state isn't actually changing much. This indicates that change detection is running on them unnecessarily often. The profiler also often shows a change detection count for each component. A high count for a component that should be relatively stable is another big red flag. It means Angular is working much harder than it needs to on that component.
Got it. So beyond OnPush and maybe dipping into change detector ref, what other key optimization techniques do our sources highlight? What else can give us significant performance wins?
Oh, there's several really effective ones.
Mm.
First, and this is almost a classic Angular optimization,
Mm.
using trackBy with ngFor loops.
Oh, trackBy. I've heard of that. Why is it so important?
Okay, so imagine you have a list of, say, 100 items rendered with ngFor. If you update just one item in the underlying data array, or even just reorder the array without trackBy, Angular might tear down and recreate the DOM elements for the entire list. That's incredibly inefficient, especially for large lists or complex list items. By providing a trackBy function to ngFor for something like trackBy fn index item return item.id, you give Angular a way to uniquely identify each item. Now, if the list changes, Angular can be much smarter. It can see which items are new, which were removed, and which just moved, and it will only manipulate the specific DOM elements necessary, often just rearranging existing ones. The performance difference can be dramatic. I remember debugging a sluggish table once, spent ages, and it turned out adding trackBy was the fix. Huge difference.
Wow. Okay, so trackBy is crucial for lists. What else?
Next big area. Reducing bindings and computation in templates. The basic idea is simple. The less work Angular has to do during each change detection cycle, the faster it will be. So a few techniques here. One is pre-calculating values in your component class. Instead of doing complex calculations directly in your template binding, like calculate total items, do the calculation once in your component code, for example, in init or when data changes, and store the result in a property, like this. Total equally calculate total items. Then just bind to the simple property.
So you avoid running the calculation on every single check.
Exactly. Another powerful tool for this are pure pipes. Angular pipes marked as pure, which is the default, are memoized. This means the pipe's transform method only reruns if its input reference changes. They are fantastic for things like formatting data, filtering lists, sorting lists directly in the template, because the calculation is automatically skipped if the input hasn't fundamentally changed. And related to pre-calculation, generally try to avoid calling component functions directly in your template bindings, especially if those functions do significant work, make calculations, or access other services. Remember, that function will execute on every single change detection cycle, which can add up quickly and is often unnecessary. Fetch data or calculate values once in lifecycle hooks like nginit and bind to the resultant properties.
Makes sense. Minimize the work done during the check. What about handling frequent events, like typing in a search box?
Ah, yes. That's another common source of excessive change detection. Events like key up, mouse move, or scroll can fire extremely rapidly. If your event handler triggers change detection each time, which it often does by default, you can overwhelm the system. This is where RxJS operators like debounce time and throttle time are invaluable. Debouncing, using debounce time, ensures your function, like making an API call for search suggestions, only executes after a certain period of inactivity. So it waits until the user stops typing for, say, 300 milliseconds before firing. Throttling, using throttle time, ensures your function executes at most once within a specified time period. For example, you might update something based on scroll position, but throttle it to only run every 200 milliseconds, preventing it from running hundreds of times during a quick scroll. Both techniques drastically reduce the number of change detection cycles triggered by high-frequency events.
Okay, those are great for frequent events, but what about those really, really heavy computations? Things that might actually freeze the UI if run on the main thread, like complex data analysis or maybe heavy image processing?
Right. For those truly CPU-intensive tasks that could block the main thread and make the UI unresponsive, you have a couple of more advanced options. One is using ngzone.run outside Angular. If you have a task that involves frequent updates or calculations, maybe processing data from a stream, But those intermediate steps don't need to immediately update the UI. You can run that code outside Angular's zone. This prevents those operations from triggering potentially hundreds or thousands of unnecessary change detection cycles. The key is, if and when that process finishes and you do have data that needs to update the UI, you then need to explicitly run the final update back inside the Angular zone or manually trigger change detection using change detector ref.detect changes or ngFor check.
So you keep the heavy churn outside and only bring the final result back in.
Precisely. And for the absolute heaviest tasks, the best solution is often web workers. Web workers allow you to run JavaScript code on a completely separate background thread. This is ideal for things like parsing large files, complex mathematical calculations, image manipulations, anything that would definitely freeze the UI if done on the main thread. The main thread stays completely responsive, handling user input and rendering, while the worker does the heavy lifting in the background. They communicate back and forth using a system of message passing.
Okay, fascinating. And finally, let's talk about that error message. The one that sends shivers down the spine of many Angular developers. Expression changed after S has been checked error.
Yeah.
It feels like a rite of passage almost.
Yes. The infamous expression changed after stats have been checked errors. It's frustrating when you first encounter it, but understanding why it happens is key to understanding Angular's core principles. It's not just an arbitrary error. It's Angular actively protecting you from potential bugs and ensuring predictability.
Protecting us. How so?
Angular enforces a strict unidirectional data flow during change detection. Data flows down the component tree. In development mode, after it runs a change detection cycle and updates the DOM, Angular performs a second check immediately afterward to ensure nothing has changed again as a side effect of the first check. If it finds that a value bound in the template has changed between the first check, when the DOM was updated, and the second verification check, it throws this error, why? Because if changing a value could immediately trigger another change in the same cycle, you could easily create infinite loops, and the state of your application would become unpredictable.
Okay, so it's preventing loops and ensuring things stabilize within one cycle. What commonly causes this error?
Common culprits include updating a component property in lifecycle hooks that run after the view has been checked, like an after view init or an after content init, or an asynchronous operation, like a promise resolving or an observable emitting, completing and updating a property after the initial check for that cycle has already passed. Another classic is a child component, emitting an event that causes a parent component to update a property, which then flows back down as an input to the same child component within the same change detection cycle, changing a value that was already checked.
So how do we fix it, or better yet, avoid it?
The fundamental solution is to ensure your data modifications happen before the change detection check occurs, or are explicitly scheduled for the next cycle. Often this means moving logic that modifies bound properties into lifecycle hooks like nConInit or engine changes, which run before the view is checked. If the update must be asynchronous, using the async pipe in your template is often the best solution for observables or promises, as it integrates cleanly with Angular's change detection. As a last resort, sometimes wrapping the problematic update in a set timeout, Sirico can work. This effectively pushes the execution of that update to the browser's event queue, ensuring it happens in a subsequent change detection cycle, thus avoiding the error. But really, the best approach is often architectural. Using OnPush and immutable data patterns significantly reduces the chances of these unexpected side effect changes occurring in the first place. Understanding why the error happens helps you structure your components better to prevent it.
Wow, okay, that was a truly comprehensive deep dive into Angular's change detection. We've gone from the absolute basics of how it synchronizes your UI all the way to some really powerful advanced techniques for performance tuning.
Yeah, we really covered the ground. Why it's the very core of Angular's reactivity, how that default dirty checking works, why zones are so crucial for the automation part, and then how adopting OnPush with immutable data can be just such a game changer, especially for larger applications. It really changes how you think about data flow.
Definitely. And then we explored taking that direct granular control with change detector if using detach, reattach, ngFor check, detect changes, empowering stuff, and crucially, drilling down into those performance boosters, trackBy forless, minimizing template work, using debouncing or throttling for those chatty events.
Right, and even offloading the really heavy stuff with endzone.run outside Angular or web workers. And let's not forget the tools, like Angular Dev Tools, for actually finding the problems and getting a real understanding of errors like expression changed after add has been checked error. Not just fixing them, but understanding the why behind them. It's all aimed at preventing those frustrating UI freezes and making things smooth.
I feel like you, the listener, now have a much more robust mental model and hopefully some very practical strategies for building incredibly responsive and performant Angular applications. It really boils down to making your app feel good to use, doesn't it?
Absolutely. It's about that seamless user experience.
Hmm.
And if we connect this to the bigger picture, maybe looking forward, it does raise an interesting question, I think. As our applications inevitably become more complex and real-time data becomes just ubiquitous, the norm,
Hmm.
how will developers consciously leverage these techniques? How will you ensure users always experience those instant fluid interfaces they increasingly expect without them even needing to realize the sophisticated machinery humming away behind the scenes?
That's a fantastic question to ponder, a truly well-informed thought to leave you with until our next deep dive.